we're going to dig into this split project, previously known as PCG tree, for procedural content generation tree, but I decided to give it a little better name. If you want to import this on your own, you can clone the repository or the gameplay programming repository. You can also just go navigate to the folder on github.com, download the folder as a zip, unzip it, and load the project. So what does that look like? Project split. And you can, I believe, download the entire directory in some capacity. Maybe you actually have to go up one level. And download linked file as perhaps. Either way, I recommend getting the entire repository and checking it out, because there's more stuff in here useful to you than that. And then you import it go to it whether you download and unzip the folder or wherever you keep your repositories. I keep all of my GitHub repositories in a Git folder under my user. So when on the command line, I can just go ~git, and all of my stuff is right there. Okay, excellent. So we'll go run it again to refresh everyone's memory. I did make some updates and some visual changes, yes. Close the lights, let's see. Do I have access to the lights up front? I don't think I have access to the lights on this control. Does anyone know where the light switches are? They're over there? Maybe not turn them all the way off so we're in complete dark, but maybe just turn them down. I think they've responded now. I guess this will be okay for just a little while. Okay. So what this program is doing is it's starting, like we described, with a single root, a single lead. And it is going through for each lead on every update cycle. It's checking. It's rolling a random number between 0 and 1 and either growing, splitting, or killing one of the leads. Great, and you can see this happening in real time. Now, what happens here is the split rate is about 5%. The death rate is about 1%. Right? So what we're doing is getting exponential growth. Now, at the beginning, I have each round throttled at 1/4 of a second. But as you can see, it's taking way more than 1/4 of a second now, as there are more and more game objects being placed on the screen. So if we go to Godot and we pause. Now, notice you don't see much here right now. There's not a lot of objects under the root. You have to go to remote to see what's actually happening in the game you're connected to. And it looks like we actually had way too many nodes for it to handle. So let's start it again and stop it before the nodes grow too much. Has anyone got this to run on their own computers yet? Excellent. Go. Got a couple people. Awesome. This is a good test case to see if Godot actually runs on your machine. Pause. Remote. Now you see the root has a set of growths and sprites, growths and sprites, growths and sprites, right? Each one of these are corresponding to one of the one of the small white boxes. So each small white box is a sprite 2D. Now, if you've been watching the tutorials, you know that sprite 2Ds are a way to put a bitmap image or a pixel art image onto the screen and have it be displayed. Now, each one of those are associated with a growth node, and these are node 2Ds. These, why a node 2D? Well, it's a marker. A node 2D signifies a position in the tree, 1, and a position in the world relative to its parent, 2. Now, each node, and this is kind of important to understand, and this may take a little nuance, may take a little while for it to sink in, because I bet not too many people have taken computer graphics. Raise your hand if you've taken computer graphics. 1, 2, 3, 4, 5, 6, 7, 8. 8 people out of 120 have taken computer graphics. Now, this relies on computer graphics knowledge, particularly when you're talking about how we handle positioning in 2D and 3D. You will see transform a lot. You will see transform 2D, you will see transform 3D. And these are ways to use different vector bases to show position, skew, rotation, and origin for everything that is positioned in either 2D or 3D. You can read the documentation for this. I'm happy to answer questions you have about it. Heck, we can even go through the math a little bit if you'd like. Now, this is important because the growth comes from the parent in this case. So each one of these has a global position on the screen. As you can see, there's things scattered all over the screen in our example. So they have a global position, but they also have a local position, which is their relative offset. So if the parent was considered to be 0, 0, the child would have some offset, or maybe some rotation, or some skew that's different from the parent. So when you're dealing with this tree hierarchy of nodes, you inherit the transform or the positional properties from the parent by default. And so you can do a lot of local things. Why would we want local positioning in games? Any guesses? Yeah.
There's a lot of objects that their movement is correlated with the movement of something else. Maybe there's a character that moves along with the player and then sometimes does something else different.
Yeah, exactly. Things like relative coordinate systems are very handy, particularly when you're talking about animation and graphics. Right?
Render distance.
Render distance is also definitely related, right? One of the big things, the notable examples, are skeletons on top of art, on top of character art. How many of you seen bone and skeleton models on some sort of character, either 2D or 3D? 1, 2, 3, probably a lot of folks, right? That way you can, so how that works is there's a skeleton imposed over an image, and each one of those positions in a skeleton has its own transformation matrix that's relative to its parent. That way, you can do this with your body, right? You can stick your arm out in the T-pose, and then my elbow joint has its own transform. Well, if I rotate that 90 degrees around the y-axis, I do this, right? And then I can rotate my wrist 90 degrees around z-axis and do this, right? So that way you can have all these relative positions, but when I move my shoulder, all of the elbow and the wrist stays the same. So you have this hierarchical decomposition that helps you handle the computational complexity of positioning. This is how inverse kinematics works. This is how kinematics works, forward kinematics, meaning motion on skeletons. And if you want a little bit more of this, you can take particularly Michael Neff's computer animation courses, or luckily, if you're lucky, his graduate course on computer animation, which is a fabulous thing. Right, so these nodes are positioned relative to their parent. This simplifies our process a lot. We don't have to reckon where something has to be in its global position when we place it. We can rely on the fact that it has a parent that has a place in the world and go from there. All right. Now, once again, we have a world, which is our base coordinate system. This is the transform that means the middle. This is center of our world. This is 0, 0, 0. Our background, which is the black square. Looking at it, it has a texture. This texture is a black 16 by 16 rectangle, which you can see in the assets folder right here. We also have a white 16 by 16 rectangle for each of the growth points. Our camera 2D is pointing at the world, and luckily you can see what the camera can see by this purple rectangle. And if you look at this in a 3D project, which we'll do soon, you will see that it's actually a frustum, which means it is a three-dimensional object where it has a flat, square, small surface towards the edge of the camera and extrudes out in perspective and then has an end plane, a back plane, which is also flat, parallel, or perpendicular to the line of vision of the camera. Now, when you look down at this on 2D and everything is projected, or 3D is projected into 2D dimension, it just looks like a square or a rectangle. We have our panel controller, and we have a label. Couldn't really see that earlier. Let's see. If you double click on the %, it'll go to 100. And you can click on any of these items and you hit F, and it should center on the item. Where are we not centering? Fine. Not sure why my shortcuts aren't working, but my computer is a little suspect right now. So it says default text, which you can see in the label over here. So that's our basic setup. But the important part are in our scripts. We have two scripts, grow and tree HUD. The tree HUD is simple. Control-Shift-D is a little hard to do with only a right hand. All right. Can you all read this code okay? Need a little bigger? I'll make it just a little bigger. So this extends panel container, which means when I created the script, I created on top of that panel container. So it's attached to it, which you can see. Okay, Control-Shift-D. Okay, there we go. Has a script icon associated with it. Right, and you can associate your scripts with any number of nodes. It has a ready function, which I deleted the pass, which is unfortunate. And it has a process function. So who knows what ready and process are? One of the basic script functionalities from Godot. Yes?
I mean, so ready is when it enters the scene. I don't really. All I've done is some basic tutorial, so I'm not quite sure. But
Sure, yeah.
and then process runs something like every frame. Gives you a delta so you know the time that it took to process like the last frame.
Exactly, that's roughly right. There's a lot of nuance in each of these, but you got the gist. And you can get some documentation on these by simply, you can right-click them and look up symbol. Boom, built-in documentation. Called when the node is ready. It's pretty ambiguous, right? That just means all the data structures that the node relies on have been filled in and instantiated, and it's been associated with its parent. So we know that all the way from world, all the way down to the tree where this node is, and everything that node depends on or touches, has been made ready. Meaning there's no null pointers unless you make them in your own code. There's nothing that will not be accessible. Everything should be good to go. So you can treat that as like your init function. Right? That's when you can really start messing with the data structures and manipulating properties. And process. This is your update. This is the physics process. And delta is the amount of time since the last physics process. So now you know how much time has passed since the last time this function is called. And that really helps, right? Because let's say you want something to go at a certain speed. Let's say it's supposed to move 1 unit per second. Well, instead of keeping track of how many seconds have passed on your own since the last movement or doing something more complicated, all that you have to do is take speed times delta, which is the fraction of speed given the fraction of time that delta represents, and you move that small increment. This is great because games used to not really have this tech. My dad, he had an Intel, one of the early Intel machines, like, I don't know, the 90s. And it had a button on it called Turbo. And that took that processor from 9 megahertz to 12. Now, we had a bunch of DOS games. Guess what happened? The game sped up, right? It was now 30% faster than it was before. That made some games unplayable, right? So these games used to be tethered to the hardware. And so we just talked about this in gaming news up today too. That means the games were probably written at which level? Any guesses? In our spectrum.
Assembly.
Yeah, it could be close to hardware level, but it could also be at the operating system level. I think the operating system may have also been dependent on the clock speed as well, right? So, luckily, we are sophisticated people, because the world is very sophisticated in 2024. We now have delta to work with. Okay, and I'll go a little bit into script soon. I'm going to talk generally about this. So we have if manual. So manual here is one of our exported variables that we talked about earlier. So we have export tree seed, int, grow chance, split chance, timer, manual bool. Now each one of these variables are typed, even though grow chance, split chance, and timer don't look like it. The type of each variable is inferred by the thing on the right-hand side. I guess particularly if you do that. But you can type your variables with the prefix colon syntax. Right, how many of you have used a syntax like this before in programming languages? Prefix, data type syntax. Yeah? Which language? Which language did you use it in? Kotlin? Yeah. So this is now the popular, more accepted way of typing data structures, of typing your variables. That way you can do inferred typing and you still have the option of being explicit. All right, split chance, timer, which is our throttle at a quarter of a second, and manual. So looking at this, you can see, going back to when I click on root, which has our script attached to it, you can see that there's tree seed, grow chance, split chance, timer, and manual. So let's turn manual on, see what happens. And I need to adjust the screen size. I was playing with the resolution earlier, and I made it too big. So the seed, the label is actually up here a little bit. I can fix it in a moment. It was one of these last changes I did and couldn't test it on this actual display. Oh no, is it actually working? Fine. Manual on. Okay, let's just look at it real quick. Apparently something is a little askew. So manual takes an input action. So if the input action, if manual is toggled and the jump button just has not been pressed, we get out. And if not manual, we rely on a time counter. So let's see, the time counter should be quite functional. We change it to 1. There'll be 1 second per update. take that off. And we're going. Exactly 1 second per check. All right. So manual just makes each check go on a spacebar press. And the timer just uses a little timer logic. So we're counting up. We have a current time counter, and if it's less than the timer amount, we add to it and return. Get out of the function. Don't do any updates. So this delta is helping us accumulate a chunk of time. And when that chunk of time is more than current time, we're off to the races. And then once we've accumulated enough time, we set current time to 0 to reset the counter. Then implement a round counter, which you can print in the console if you so choose. And now let's get into the bulk of the code here. We have a remove list and an add list. We'll see what those do later. We have at the top leaders, growth scene, number growth count, current time, and a round count. So we're using all these variables. The one here, we're actually taking the growth scene, which is very simple. This growth scene is simply a white square. If we look at it at the scene view, it is a node with a sprite. Exactly what we need for this tree. Our root scene is just a root with a script on it. That script is our grow script. So we're preloading that scene. So what preload does is it means that scene has been processed and we're ready to use it. So by the time growth scene gets, it makes sure that there's a block. So you cannot use growth scene, or this ready is not called in this function until this preload happens. So growth is loaded. On our ready, we set a seed, the random seed for this particular tree. Change the seed, change the tree. We get our very first growth. We're calling instantiate. So you can treat scenes like classes, and you can instantiate new versions of them. And we're adding that to our leaders list. So this is all of the places where the tree can currently grow. And then we add the new growth to our display tree. And it should be noted that this is the object, the node that the script is attached to. In this case, that's our node 2D in root. It is our root. All right, so that's our setup. Plunk a node down, get the lead, get the leaders ready to go. Our process delta, we talked about this portion. And here we're just simply counting up the number of rounds of growth that we've had. We have a remove list and an add list. And if the leaders get to 0, we print the tree is dead. It's very sad. Now, for every time we run this process, every time we get through our checks, our various either manual or time-based checks, we call a random value. So we've initialized our random number generator, or Godot's random number generator, with the seed. And then we call randf, which gives us a value between 0 and 1. And what we do is first we check to see if the random value is less than the split chance. So is it less than that 0.05? And if it is less, that means we grow. So what does growing mean? Well, that means adding 2 nodes to the scene instead of 1. We have the original node that we grew from, and we're branching a little to the left, a little to the right, rotating them, and placing those on the tree. So, left growth, node 2. You can do the same thing here. I was just showing that you could do automatic inference here with right growth, and it works just the same. We take our growth scene, and we instantiate 2 new versions of it for left and right. And we add, the leader here is now where we want to grow from, not the root, right? So the leader that we're growing from, we add left growth as its child. And then we set their transforms to be the same. That means they're now at the same location, have the same rotation properties. But then we want to rotate that left growth just a little more. And we want to move it in up direction. Well, this is interesting, right? Because up isn't global, up is local. Because we rotated, growing up is slightly rotated as well. That 0, -1 displacement is now relative, is now filtered through its transform, which has a rotation in it.
Question.
Yes?
It's relative to the order of the code, right? Because like if you called the translate up first, it would just go up and then rotate, right?
Yeah, and then you'd rotate. Translate changes the origin, so you would then just rotate in place. So I think these two they're a little different, right? You would grow then rotate instead of rotate then grow, so there'd be a tiny difference in that first growth node of the tree, and that would be the same there on out, but there would be a difference. You probably would have to print it out to see it, but it would be there. Good eye. And then we do the same thing with the right growth. With the right growth, we just rotate a little bit in the other direction. And rotate here is radians. There are functions, there's definitely degree to radians, all the math stuff you're used to. And then we translate it in its up direction as well. Now we add the leader to the remove list, and we add append. We add left growth and right growth, we append those to the add lists. Now remember the code example that we saw on the first day of class? Where it had removing and adding items in an array while we're iterating through the array? Well, this is the pattern to not do that. This is the way to not do that, right? You just simply add a post-processing list of adding and remove, a delete list and an add list. Right? And so we just cache those up, and we go through the list, the unaltered list, and then below we remove and add from the leaders. Right? Pretty simple stuff, but it'll save you a lot of heartache when you hit one of these errors eventually. All right, now if the random value is less than the split chance plus the grow chance, right? Because we want to make sure we preserve that distribution, and we want to make sure that we're hitting the slightly greater than 0.05 and less than the 94, which is the grow chance, plus the split chance. So we're shifting down into that 0 to 1 space a little bit of causality. And we add a new growth scene, or we generate a new growth. We add it to the leader. We give it the transform of the leader, so it has the same rotation and position. And that way, when it grows forward, it grows with that rotation. That's why there's a curving motion when the tree grows. And here we are actually transforming the origin. So this is important because you want to account specifically for origin transformation, because if you do translation, you actually get a compounding effect. And each subsequent child is a little further away than the child before. And you will get very large distances between nodes if you do move local Y or translate. And then we add the leader to the remove list and add the growth to the add list. Right? Here's our failure case. If it doesn't grow or split, it goes away. If all the leaders go away, tree is dead. Did you have a question, Nick?
Yeah, actually, for those two statements, will both of those triggers have like a random value of 0?
Oh, this should be an else if. You're right. Good eye. I must have changed that at some point when I was testing. Thank you, Nick. So those would have triggered as the code was. Yeah.
So can I go down a little bit? Like,
Say when?
yeah, right now. Okay, so like when you're like removing, like you're adding the leader to the removing and the adding the rows to the atlas.
Uh-huh.
Can you just like at this point you remove the leader from the atlas at this point? Or just like at least stop remove or erase leader because
Okay, the leaders is the list of everything that's growing. The add list and remove list are modifications to that leader list. So if we go below, our add list simply adds whatever's in the add list in this one particular round through process to the leaders. Yeah.
It's just like the leader that will be removed is recorded in a list, and then later it will all be removed.
I believe so. I didn't quite get all, I think, of the intent of your question. If you'd like to restate it.
It's like we don't remove the leader immediately, and we recorded it in a list, and then we remove it at once.
Exactly, right? So what, to restate so everyone can hear it, we are recording what we want, how we want to modify the leaders list. That's what remove and add lists do. And so all these leaders, the new growth is now the new leader when it goes up straight. These splits, these two left growth and right growth are the new leaders. And so we add those to the add list, which then makes them added to the leaders list at the end. This way we don't change or manipulate that list that our loop, our iterative construct relies on. So we do not break our invariance with side effects while we are programming. I realize I haven't looked this way in a while. Sorry. Yes.
Can you explain the transform origin part of it? Why couldn't you just do the other transform thing?
Because perhaps, okay, so this is equivalent. I think what I was doing is actually showing it a separate way. So I hadn't quite grokked all the reasons why yet, so I had a little mystery when I was programming this a couple nights ago of why this wasn't working. So what I was getting was a cumulative effect. So for instance, round one, all the growths would be 1 pixel up when I was going by single pixel coordinates. Then round two, each new growth was then 2 pixels from its leader. Then the next round, at round three, they were 3 pixels above the leader. So the distance between leader and new growth was growing cumulatively every round. And there was some effect with translate and move, local x, in the growth function that was causing this side effect. And I hadn't quite grokked exactly what was going on there. But me knowing how the transform works, I just immediately manipulated the actual origins to put things where I wanted them. When I have the time, I will investigate further and find out exactly what's going on. But I haven't had that time yet. All right, should we make a different tree? Are there any other questions about the script? Is everyone understanding all the parts here, the nodes, the scripts? This is meant to be a pretty approachable example as far as the Godot contracts go, but it's meant to be a meaningful example as far as the code goes. That way you can see, 75-ish lines of okay GD script. Yes?
Instead of add child function, is it like is that a building function?
Yeah, add child is the built-in function.
Okay.
So every node can be placed, so node means it can be placed on the tree. And everything that is hierarchically under the node in the class hierarchy has the ability to be put on a tree, has a transform, and knows child, parent, and sibling relationships. Okay?
Can we find this script later in the website?
The
The
Yeah, it's already in Gameplay Programming's GitHub repository in the projects folder. And I'll upload the recording. We kind of went through that a little bit earlier. All right, so going to the root. What's a good number? Someone give me a number, an integer. 34. We can do 5 next. Let's see what type of tree we get. Oh, I'm actually going to speed up the process. This is I guess I did have it at 125. Let's go faster. And something to note is that if you change the growth chance and the split chance, you will not get the same tree out of the same seed, right? That sort of changes the procedure to generate the tree is different. You get the same numbers from randef, but they'll be interpreted differently. I'm sorry? No, it's going. But it didn't seem like it respected the new time, did it? Oh, the timer is 01. Let's just take off the timer. Save. Yeah, that's what I don't think I saved. Go, go, Godot. I imagine your machines are all much newer than my 2016 MacBook Pro, so you may be experiencing much more quick response. Maybe this is just as slow as my machine is right now. Maybe we'll see a different tree. I thought I had the manual mode unchecked. It wouldn't be growing. It did. Right, so it's definitely a different tree already. But you can see each growth. So there's already much less splits early. So you can see how each node is a distance from the previous. And we're growing in small arcs, which is consistent with our small rotations. I must have introduced a bug. One moment. While we just simply... Here's a handy shortcut for you. Command // comments an entire thing you have selected. Command B runs the project. Command R runs the scene you're in. Control if you're on Windows. Instead of command. And we'll be done in just a moment. I want to make a quick, there we go. Now it's nice and fast. There's our new tree. Let's make it so we can actually see it. Yeah, the lights are on. Well done. I will be having office hours tomorrow, starting at 11 for this class. I will have general office hours starting at 10:30 because there are some folks that wanted to talk research. But these will be held on Discord. So you can come in and go to the office hours channel in our class area. Thank you, Nick. And we'll take it from there. I will record that session and post it as well. Because it's office hours, I will just put it on Google Drive and not on YouTube. I will post this on YouTube. All right, one more. I'm going to change the scaling of the root. We'll make it a little smaller so we can see more of the tree. Yes, so if you would like to go to the Game Dev and Arts Club, follow Jasper. I'll be going over there on my bike as well, so I'm happy to see you there. There we go, whole new tree. and you can see more of it. Yeah, one moment. I can do it off this. I want to stop recording first. All right, thank you all. Excellent first discussion section. We'll get more of the kinks of this room ironed out, and it will be even better next time. Thank you for your patience through the technical difficulties today, and we'll see you all on Thursday. Thank you.